Hello, everyone. Welcome to this session. I'm going to do a little bit of an introduction because it gives me great pleasure to introduce Yannis. Yannis Papakonstantinou joins us from UCSD. Some time ago, I was a grad student under him, and so he's my advisor. And so the database geek in me was very, very excited to hear about SQL++. We're here today at this session to learn more about SQL++. So with that, let's welcome Yannis. Yannis, thank you so much for joining us, and take it over.
Hello, guys, and here is the message that I'm going to send. You have heard these days about JSON, a database that is using JSON and uses it in a very, very efficient way, making really scalable applications. And you must have also heard that NoSQL is moving towards becoming a fully declarative language. Okay. And the message that I would like to send is that I see that in a bunch of years, a combination of all these things where you can have it all. You can have JSON, you can have scalability, top performance, and do your querying in a declarative fashion. Do your analytics. That's where most of the more demanding queries are, in a declarative fashion. And at UCSD, we have a query language, SQL++, that looks strikingly like NoSQL. And I'm going to talk about it in this context that we see here on this title. And there is a paper that has been handed out along with the package of the conference. And this paper is actually describing in detail SQL++, which is a product of Kian-Hui Nong, Romain Vernou, and myself. And also many applications have been built on it by the people that you see there at UCSD, Computer Science and Engineering. So let me give you a quick preview of what we're going to do here. We will discuss what is SQL++, what is the principles behind it. We will discuss how we use it in UCSD's Forward project, because actually it's quite surprising. Here you have been talking about NoSQL and JSON in the context of databases and scalability. We come from another context of integration and live analytics. And you will see that it all fits together. I see a great future basically for JSON and declarative queries combined together. Then I'm going to give you a quick introduction on how you should read this formal SQL++ paper and the survey that we have got attached to it, that is where we formally rank the expressiveness abilities with respect to JSON and with respect to declarative querying of 12 systems out there, formally so. And I will give you a taste of it and tell you how you can read the rest of the paper. And of course, we will discuss the NoSQL connection. And it's a really good news because at this point, the NoSQL is the closest, is the industrial twin, really, of SQL++. And it will become much more so, I believe, very soon. From discussions I had with Gerald, who is here and is managing the NoSQL development at Couchbase. So let's start. What is the principles of SQL++? So on SQL++, we wanted to generate a query language whose data model is simultaneously a superset of JSON and SQL. Next, using this data model, we designed a fully declarative query language that can simultaneously query SQL and JSON data. And this language is ++ because it is aggressively backwards compatible with SQL. Okay, that is whatever is done, is doable with SQL, happens just with SQL. Of course, there is plenty of extensions to capture the points where JSON goes beyond SQL, and you need special abilities in order to access JSON and in order to construct JSON by your queries. Now, we delivered on this in a number of steps. The steps being, we have a formal semantics that you can actually read on the paper. The key element of this formal semantics is that basically we adjust tuple calculus, which is the theoretical base of SQL and the formal base of its semantics. We adjust it to the richness, the semi-structured nature of JSON data. That is step one. Step two, any language is good when it can be implemented, and any declarative language is good when it can lead to automatic query optimizations and automatic query execution, planning and execution. And we have done this not on a database setting, but on a virtual database setting, that is in an integration engine, a virtual database that can sit on top of a SQL and NoSQL database and integrate data between them with federated queries or materialized views. We'll talk a little more about it. So you will hear a little bit about the use of SQL++ in federated queries, the use of SQL++ in automatic incremental view maintenance. Okay. So the next topic I would like to go into is go a little bit in the detail of one thing, because it is so easy to show that what we could achieve with what we achieved with the SQL++ data model. So notice that the SQL++ data model is a superset simultaneously of both SQL and JSON. You may think that it is JSON with bugs. A bug is an array that doesn't have an order, right? And enriched values. Okay, so floating points and images and so on. And on the other hand, you may think of it as SQL that also has arrays, which is basically ordered sets, has nestings. A tuple may have its own collection of tuples and so on, and has heterogeneity in the sense that your objects do not need to subscribe to any rigid schema. And here you see an example. So here you see that could be a possible database. You see here one JSON object if you want to say it as JSON object, SQL tuple if you want to say it as SQL tuple, that has got a bunch of attributes. It has location, it has readings. Cool thing, the readings, notice it doesn't have a scalar value, but its value is a nested collection, an array in particular, as denoted by the brackets, of other SQL tuples or JSON objects, whatever you want to think of them as. Notice that these data are heterogeneous. For example, the first tuple had nitrogen dioxide, the second one had carbon monoxide attributes, right? And you see each one carries its own attributes. And notice also that I have not highlighted this, that as far as JSON is concerned, we have also enhanced it with the ability to have some enhanced types. For example, here this says, think of this as a timestamp type. Okay, so and that's really, with this thing, you practically know most of SQL++. Okay, so now the goal is to have a query language, as we said, that can do the following things. Number one, extend the SQL syntax and semantics for the respective data model extensions that we did. Which extensions we did? We say we have heterogeneity. We said we have complex values. We have arrays. We have maps. Actually, I didn't show you maps, but we do have them. So we have correspondingly to open up the query language. So this query language allows you to nest and unnest, so that you can create and access nested collections. It goes beyond SQL. SQL always talks about tuple variables. And here, you could have an array that is just an array of scalars, for all you know, right? You could have all sorts of things. You could have an array of arrays, right? And it becomes very important then in the semantics to go beyond tuple variables and really talk about element variables that can range over anything, scalars and scalars, arrays, bugs, maps, and so on. And multiple forms of navigation will be required because, again, it's not only from a collection of tuples I go to the individual tuples, but it could be that from a map I go to the elements of the map. From an array I'm indexing by number to the relevant position and so on. So we have all of these extensions. The bottom line is that we have queries that can input any kind of JSON data and output any kind of pattern of JSON data. Finally, there is an extension that is very particular to our project that has to do with the fact that we are building a virtual database that wants to have universal access to multiple databases like Couchbase, MongoDB, SQL simultaneously. I'm going to come very briefly to this later. But the most important points to keep are the top ones, because I believe are the kind of stuff that will apply to basically anyone who goes into semi-structured data and declarative simultaneously, be it for a database, as Couchbase greatly does, or for a virtual database. Now, let's skip this one. Let me briefly talk on how we are using SQL++ in UCSD's forward project. And the fascinating thing is that we're basically using it in different cases than Couchbase. Couchbase is using it as a database. We are using it as a virtual database and as an application development framework for rapidly building live analytics applications, primarily live analytics applications. And that's actually a proof of concept here in the sense that I believe that the future across the board should be semi-structured models, right? And I think we're proving from many sides here that you can have a semi-structured model while you also have declarative querying and the requisite performance along the way. So the number one basically use case in which context actually we came up with SQL++ says the following. Imagine that you have got a bunch of databases, a SQL database, a NoSQL database, could be Couchbase. You even have some Java main memory objects on your memory space. And now you want a client, and this client would like to basically integrate issue queries that integrate data from multiple of these sources. How do you go about it? Well, basically in forward we say the following. Look, we have some wrappers. Okay, and what the wrappers do is that they sit on top of each one of the sources and they provide a SQL++ virtual view of the underlying source. Okay, obviously being very easy to do this on a genuinely SQL or genuinely JSON source. And the next step that is coming in is that optionally, if you'd like, the next step that could come in is that basically the client can issue a query against a federated query against multiple of these data sources. So it issues the query, the processor cranks out basically an answer to this query by combining data of multiple sources. In practice, you may want to do this a little more consolidated in layers, and you may want to provide some SQL++ integrated views that basically reformat the data of each source to the needs of your application, or actually package the data of multiple sources according to the needs of your application. The most typical case, for example, a very typical case, for example, you will see about it comes in customer relationships management. You have a company, it has one database that has a CRM data, another database that has a web log that is on a Couchbase. You want to build an integrated view of the two, some data in the SQL, some data on the Couchbase. Well, you may want to build some SQL++ objects that stand for the whole package about each customer. Both his CRM data as well as his web log accesses and aggregations, perhaps, about them. Okay, in which case, the picture can become a little more simple for the client, where the client issues queries to the integrated views and gets back, the SQL++ or JSON data, whatever you want to call them, that he asked. Keep in mind, these views could be purely virtual in the sense that they are just a view definition. they're just a view definition, and wait a minute, what happened here? An SQL++ view definition, or they could also be a materialized view in the sense that you're basically saying, hey, I'm giving you a view definition here, but really materialize it in a database. Okay, and we'll come to this more later. Okay, and there's plenty of use cases on why you would want such an integration system. One thing is because you may want to hide the source features of other systems. For example, if you have a MongoDB, its language looks really mysterious, very far away from SQL. Well, you could cover basically the MongoDB behind this interface that gives you SQL queries and SQL results while you have encapsulated the MongoDB into the relational view of your preference. Another case would be that you truly want integrated query processing. So really, you have an SQL database and a MongoDB or a Couchbase there, and you're issuing basically some queries that access both in order to get the results. And let's see an example of this case. Let's assume, for example, here that you have got some sensors at some, and you know from a Postgres database their latitude and longitude, and you have got on another database, on the MongoDB, you have got measurements by a sensor. So you see there, sensor 2 at temperature 70, sensor 2, temperature 49.2, and so on, right? And you may have a query. The query up there says in SQL++, I want the sensors in a given area that recorded a low temperature. What the system will do with respect to this is that it will basically decompose the query. It will send a query down to the SQL database to find which sensors are in this area. And then comes the interesting part. It has to send the query to the MongoDB. Now, MongoDB has really odd semantics. And notice that this less than, that looks quite innocuous, right? Less than 50, right? I mean, what can go wrong with less than 50? That has one meaning. Well, no, wrong. It doesn't have one meaning. Because to find out what kind of meaning it has, you have to consider all the details. What's going to happen if the temperature is missing? Because we talk about semi-structured data. What will happen if the temperature is null, right? So here, why did I go into this example? Because I wanted to talk about the last feature of SQL++ that we added. I said we have one that is particular for integration, and is basically the fact that we are capturing semantic variations by having effectively configuration settings in front of predicates, in front of functions, even in front of SQL clauses. So for example, we want to capture the fact that it's one thing the SQL less than, it's another thing the MongoDB less than. And we do this by a system that we describe extensively on the paper that is basically configuration settings. For example, the configuration setting of MongoDB when it comes to less than says on complex I can return a Boolean, but on type mismatch I'm always saying false. On null, less than null, I'm always saying false. And on null, less than value, I'm strangely and unlikely SQL, I'm returning a Boolean, right? So keep in mind these config parameters when we come back to the survey aspect of the paper, because when we classify formally all the databases out there, a lot of the classification is based on these config parameters. Okay, fine. And there's plenty of semantic variations in the systems out there, in paths, equality, comparisons, selections, grouping, ordering, set operations. So there is corresponding classifications and config parameters that you will find on our paper if you want to find out what each system does or doesn't do, actually, sometimes, with respect to these things. Okay, I'm going to pass the next use cases very quickly. The next use case says that, another thing that we do is that you have systems that have limited query capability. So basically what this software is doing that we have built is basically often bridging the limited and different capabilities of the underlying system. So you got a system that cannot do joins. Well, okay, we bring the join to the middleware. Fine, let me pass the last one to go to our next use case that we actually like very much. It is basically incremental view maintenance. And then you will see how we went into incremental view maintenance, but let me first tell you what is incremental view maintenance, because it's a great functionality that you can have. Fully automated incremental view maintenance is a great functionality that you can have with SQL or SQL++, with declarative, basically, systems. So on the problem is the following. You are given a SQL, you have already, let's say, a Couchbase. Okay, you have a semi-structured database. Okay, and now you are given a view definition. Okay, what is a view definition? For all I care, a view definition is simply a query, right? It's a query that is basically saying, take as input this database and produce as output this view. Okay. And when you first give this materialized view, the system really does this thing. That is, it really materializes the view that you see there. Okay. So an example, why would you build this is, for example, you have a web log where in this web log, for some reason, every time that you are sending a page that shows some list of products to a user, you really put it on the log. You know, I showed to this user this list of products. And perhaps then you want to have a view that puts added value to this data by basically saying, hey, I want you to organize for me collections of tuples that have, each tuple has a product category, the count of accesses that happen for products, the count of how many times the products of this category appeared, and for each product its individual count, right? That is something that you could have asked. Now, what do you want from incremental view maintenance? Naturally, over time, you're going to have a stream of inserts, deletes, updates on your base data, right? That is, the web log will get more and more stuff. Perhaps you may delete as well some stuff. Okay. Now, obviously, you can say that, you know, I can go every night and reconstruct the view. Okay, of course, then the view, that means that from night to night, the view is not going to be up to date, right? Plus, you run the risk that one night may not be enough to recompute your view. Where is incremental view maintenance comes in? An incremental view maintenance algorithm says, okay, it says, do for me the following. Figure out an alternate stream of updates, which I'm calling here the IVM stream, so that by applying this stream of updates to this view, to the view before, you can end up with a view after very efficiently and very automatically, because it's going to be incremental. Okay, and these things can happen on SQL. And I had heard silly arguments of the kind, you know, that is the reason why you don't want to go semi-structured, because, you know, if you go semi-structured, you won't be able to do this kind of things anymore. And that is totally false, right? The same principles that applied in relational, you can apply them on semi-structured, on a declarative language. Yes, we did have to do some extra work to pay extra attention to the fact that typically in these cases you may have replication of data in views. For example, what if a product here belongs to multiple categories? Yeah, you got to do some clever tricks there to boost the performance further. But there is extra opportunities as far as I'm concerned when the database has keys as a prime citizen in it. But that's all good, actually. It's extra opportunities rather than being something that was doable before and is not doable now. And to show you a little bit of to add a little visualization in this talk, we actually have used the incremental view maintenance in custom analytics dashboards and interactive pages and applications. And it's, again, it was such a wonderful fit for JSON that came from a different spin from the one that you see usually. So our key observation here is that the data models of your usual visualization components, you know, being a Google map, a high chart, and so on, can be very nicely and very easily be captured with JSON models. Right? You may think about each one of these visualization components as if at every time it visualizes some JSON structure. Okay, and then if you start thinking like that, then next thing you may think about is that your whole page is just one big JSON SQL++ view, right, that creates the JSON that is being displayed on the page. And that's great if you think about it like that, because now you can feed your whole analytics out of a single query that is feeding the page, and by utilizing the incremental view maintenance, can keep the page automatically updated as the underlying data change. And let me show you a very little demo about it. Consider Google Maps, right? The Google Map has, in our system, a data model that can be described in about 45 lines, where key parameters of it are captured in this model. Here you see the basic one that says, hey, Google Map has markers, and each marker has positions with latitude, longitude. There is, as I said, a few more, but we don't need them in this demo, so we're not going to go into it. Now, look at this thing. This is our online ID of forward. Actually, we have built the ID itself on SQL++, just to make sure that we like our stuff so much that we can even build the ID on it. And here I'm going to show you a little page that shows cars moving, and I will show you how easy it was to get to this page by thinking in terms of JSON. Okay, so this is my neighborhood, a mechanical engineering professor. Sorry, it works out of my phone, the connection at this point. It's a little slow, the Google Maps, with my Verizon. Okay, so here what you see on this demo is that there is a database that has got cars in it, and there is a stream of updates coming into this cars database, and basically the map is moving as the cars are moving. Okay, that's my neighborhood, actually. So how many lines did it take to build this thing? Actually, just that few lines here. That's the Google Map. So notice what this thing is saying. It says that, look, I have a Google Map. That's the thing I showed you before. It has markers. The markers are coming out of a SQL++ query that says select ID lat long from the cars that join with the session zip code. I have already set the session zip code here. And then I'm simply basically instantiating the latitude and longitude of the positions, right? You may not directly see here the SQL++ simply because we put a little syntactic sugar on top of it to make it look like JSTL, like a markup language. But it's really just one SQL++ query that instantiates a JSON object that gets incrementally updated the way you see it there. So again, as I told you, a use case that is not the kind of thing that you've been hearing these 2 days, but nevertheless, yet another great use case for JSON and semi-structured. So with this, I'm going to move to the, I hope I convinced you that JSON and declarative queries, declarative views make a wonderful mix together. And I'm going to move to the next thing, which is how to read this paper with the SQL++ formal specification that we handed out in your package. So how many of you have read the Da Vinci Code? Yes. This is nothing like the Da Vinci Code, unfortunately. The Da Vinci Code, you open it and then you go page by page. This is more of a reference material, right, that you are going to go to one section at a time. Now, there is, however, 2 essentials that I suggest that you read, because once you have understood this, you can jump everywhere. The number one essential is the data model itself. I presented the data model before. You will find it in sections 3 and 3.1. Then we talk about schema and flexible schemas and so on, but you can, for example, totally skip that part and go to the query language. Now, when it comes to the query language, what is very important to understand is it's just one thing. If you understand 2 pages, the other 30 pages will just flow. The key point is the fact that the language is extending from the tuple variables of SQL to what we call element variables that can bind into any kind of JSON, not only JSON objects, right? And then once you think about element variables, the select from, where, group by, order by, limit, etc. semantics become basically a pipeline where bindings of element variables trickle from clause to clause. And for example, consider the query. For reasons that will become obvious, we have the select clause at the end, and we start with a from clause. Imagine that you have a database that has readings. And the readings is just an array, the way that you see it here, just this array. Okay, guys? This is the so-called initial environment, the database itself. So now, I'm saying from readings as element variable R. You may think of conceptually at least, of this from clause generating a bag of bindings of R. Okay. The where clauses do, these bindings could every time have multiple element variables. It just happens on this example that it is only one. Okay. The where clause, what is the where clause doing? It disqualifies the ones that don't satisfy the conditions, right? What is the order by clause doing? Well, it orders them by the function that you have got here. What is the limit doing? It keeps the top, right? And notice that the order by also changes it from bags to arrays, because now an order matters here. What is the select doing? The select is packaging them, right? And here it is the select like SQL select that basically says package them into tuples, so it packages them into an array of tuples coming out. That, if you understand this concept, that basically the SQL++ works as a pipeline of clauses that send element variable bindings from the one to the other, you can basically jump in any section of the of this formal specification individually. Okay, here I got a query that is slightly more complicated. It has nesting, right? We said it's a very critical feature for when you deal with JSON data to be able to navigate into nested data, you know, collections that have whose tuples have their own collections. It's also important to be able to construct such data. So for example, here you see a database called sensors and logs. The sensors is giving me sensor IDs. The logs are here in this case just because in the form sensor1 carbon monoxide this, sensor1 carbon monoxide this, and so on. Keep in mind this could have been nested just as well. I could have written this example by nesting all the carbon monoxides under a single sensor reading. Now I want the output to look like that, basically do the nesting. Okay, that is have for every sensor, have the respective readings. And again, how am I doing the job? I'm going from sensors as, and I'm binding to sensors. You see the bindings of sensors coming in. Now I'm going to the select. The select has a nested clause. You may now think the nested clause operates once for every binding here in the environment that is constituted by this binding plus whatever other bindings I could recursively have from the environment. Okay, and you keep going. So basically here the from is pumping up the way that you see here. For example, the join is using inside, outside, inside query, outside query bindings simultaneously. Okay, so if you get this concept of element variable bindings, everything else flows pretty easily. We also explain features like Couchbase's flatten and flatten, also in terms of how you basically could simulate them with these binding element variable based approach. Okay, great. Next part. Introduction to how, wait a minute, one step back. Once we did this, once we provided this formal specification, and on the same time, we had studied all of these NoSQL, NewSQL, SQL and Hadoop databases that are out there, and we had seen how they differ, and we were using this thing of how they differ in making our virtual database engine. We thought, and many people told us actually, hey, you have a lot of stuff about how to formally compare all of these systems out there. And we set out to do this. And in the paper that you have, you will see that we compare 12 systems. One of them, of course, is standard SQL, but the other is Couchbase, MongoDB, and so on. Formally, based on the semantics that we have given to SQL++, which is actually a superset of all of these languages. And utilizing a lot the configuration settings. Again, this is not the Da Vinci Code. You're not going to read it from start to end. You will probably jump into the sections that matter to you when you work on a particular feature. So I'm going to give you here, this is the stuff that we covered on the paper. So again, I'm going to give you an example of how to in one of these many features that we analyze formally in the survey, how to jump in one of them and get the conclusions that you want. Let's take, for example, I'm going to use here 3 examples. Number 1 example is going to be the data model comparison. Okay, so for the data model comparison, how are you going to read it? You're going to first read the formal definition of the SQL++ model. That, I think, is section 3.1. We have some examples there. Then you will see that some feature matrices that classify across multiple dimensions, which correspond to data model features, each one of the multiple databases that we compare. Okay, and the classification is usually in the following form. It is yes, this system does that, no, it doesn't do it, or asterisk. Asterisk, the text says why it is half doing it in what exactly way. I'll say a little more about how we came to this, but let me show you here an example, right? That was the example that we had seen when we started, right? So you got here a bunch of features, we said you have nesting, right? You have enhanced types, you have arrays, you have bugs, all of that stuff. You may have maps in other examples. So then you go into reading the formal specification of it. All the formal specifications, when it comes to syntax, are in form of a BNF. And the semantics, as I said, when it comes to query language, very much draw on this element variable calculus. And then you come to the spreadsheets. Okay, and the spreadsheets is the thing that I told you. For example, here you see who's doing arrays, who's doing bugs, who's doing sets, who's doing maps, who's doing enhanced primitives, enhanced types, who supports heterogeneity, composability. That has a weird name. This has to do with the fact that, for example, multiple systems allow bag of tuples at the top level, right? But only at the top level, right? So that we would consider non-composable. If basically what you have on the top level you cannot also have on the nested level, that would be a non-composable, right? So that is the pattern that you will find all across the paper. So you see here a bunch of dimensions. In this case, it's 2, 4, 6, 8 dimensions with many yes, no, and partial support points to be discussed in the partial support is usually discussed in the paper. Here is an example. Let me skip this. An example of query. That was a nested query I had shown before, right? So for close enough, actually. It says go to a collection of sensors, and for each sensor, put its lat and long, and after the lat and log, put the ozone readings that we have for this sensor. Okay, so you see it has nesting, right? You could have another query that is creating non-tuples. Here, this query is creating arrays, plain arrays. Actually, in this case, plain bugs. Again, you go to the feature matrix, you're going to read that stuff. You're going to see features like that. Who is able to do tuples containing nested collections? Who is able to do non-tuples? And so on. Okay. Many more. As I told you, we have plenty of this kind of examples, of dimensions. Very central is this thing of configuration parameters that I talked before, because at some point the discussion leads into what exactly this system means by equality. What exactly does it mean in the equality used in the group by? Because a group by has an implicit concept of equality that it uses to put two objects in the same group or not, right? Similarly, what does a system mean by less than? What does it mean by less than when it comes to order by, right? And these we have captured basically by saying we define formally these configuration settings, configuration parameters that I told you before. And then each system is basically classified according to what is its value on these configuration parameters. That was not the best example. Let me go to the equality. For example, consider the equality. On the equality, you have configuration parameters that say, what will the system do if it is asked to check the equality of two complex values? What it will do if it is asked to check the equality of two type mismatched values? What will it do if it does null equals null? What will it do on null equals value? What will it do in missing equal missing? Right? What will it do on missing equals value? And so on and so forth. So basically, the various systems are classified according to what they will return when it comes to equality according to this. And that's what you will find in the matrices when it comes to equality, inequality, and correspondingly group by and ordered by. Okay, is it clear, folks, what's happening here? Keep in mind that a special, an unfortunate special configuration value that we often have to use is the error, right? Which basically means if you give this thing to a system, it will crash. Okay, so the error, don't expect a lot of semantics. It just basically says that the system stopped working when we gave it this. All of these feature matrices that you see, we have actually tested them. That is, we downloaded these systems, we gave them little queries that would exemplify what they would do in each one of these examples. And we have these big spreadsheets that also say what are the queries with which we tested them and the data with which we tested them. And because that was a huge effort, and it is a huge effort that we will have to keep up to date. Nickel is coming with a wonderful third and fourth version that obviously updates our feature matrices, and probably others will do the same. What we're going to do now is we are going to basically crowdsource the maintenance of these feature matrices. Very soon we will release an application where basically you can suggest to us how particular settings in our metrics have changed, right? But yeah, and you can complete in our supporting matrices, what is the query that you run, to show that it has changed and so on. Of course, you will be very welcome to correct errors that we may have as well this way. Okay, great. So I hope I gave you a quick taste of how to go about reading this paper that provides the formal semantics of SQL++, which is a preview, I believe, of what we're going to see in the future, and definitely NoSQL goes there with JSON and declarative queries, and how to basically compare formally all of these systems. When it comes to conclusion, our survey basically shows that the usual marketing clusters that you see, like the NoSQL, NewSQL, SQL on Hadoop, and all of that stuff, they don't really correspond all that much to a clear clustering of fundamental capabilities on query languages. And generally, we are on a point that very few databases have advanced on the expressive declarative languages. The matrices you will see are very sparse and very fragmented. Okay. The good news for all of you who were here is on the Nickel and SQL++ connection, because actually the Nickel, if you see the survey, it's actually coming across very clear, like ahead of all the industrial databases when it comes to support of declarative, Nickel actually, just to be precise, rather than Couchbase. Nickel in particular comes across as being ahead of all the other query languages that are out there with respect to expressiveness, expressiveness in its declarative language. Keep in mind that when we were checking expressiveness of systems, we did not really expect anyone to have exactly the SQL language. We were expecting whether with their syntax, you could write the SQL or SQL++ feature that we were presenting, right? And in that spirit, as I say, Nickel was ahead of the rest. Actually, Nickel was ahead of the rest when it comes to SQL compliance as well, even on the basic syntax, though we don't really compare systems on this. So I believe it's a great thing that we met actually with Couchbase. We were doing this work on SQL++ totally independently. As I told you, we came from a different background. We came from a background of virtual databases, of analytics, of visualization of analytics. Nickel was working on its scalable database. And in that sense, it was wonderful to see such a nice alignment in principles of of both of us basically believing that a JSON-based model is the right one because it can capture what SQL has to give you, while it also gives you the rich data, the semi-structured data. And we both believe that the fact that you're going with semi-structured data, it does not block you from going declarative, right? I'm also very glad to see that the distance will be closing more and more. And I have discussed with Gerald about the release 4, and it's really on a great, Nickel is on a very great track to basically achieving a JSON declarative language that is highly compatible with SQL. Okay, and though I have gone over time here, I will take basically just one more slide to sum up, the crystal ball, and the conclusions of this talk. So I believe that eventually the future will be semi-structured and declarative. Semi-structured models and declarative, supported by declarative queries across the board, talking databases, talking virtual databases, all of this. Because you can have it all. There's no reason to not have anything of what we see there. You can have basically scalability. You have already seen this by the many talks here. You can have the flexibility of a semi-structured model, right? And schema-less, or as much schema as you want implementation. You can have the automation that is coming with a declarative language, whose statements get automatically optimized, whose statements can get logically, physically separated. I'm not saying that all of this has happened fully, that the automation or the logical, physical separation is now fully done at Couchbase. It's not fully done at our project that we do virtual databases either. But on a principle level, it is on track to get there. And definitely, I'm absolutely sure that in a few years, we will have all of this in whatever the setting is. And that's great news, right? Because when you get the automation, when you get the flexibility at the same time, you get rapid development, right? You get rapid development. And I saw a lot of black belt developers in here, in Couchbase Connect, right? Guys who know how to basically go into to write imperative code, right? That takes the key fundamental applications for the companies taken care of, right? But keep in mind that after the black belt developers, and once you have these big databases, this big JSON database and so on, there will need to be many secondary applications, right? There are going to be many analytics applications and so on. And there is a finite supply of black belt developers in the universe. And there is out of 13 million people who call themselves IT people, 3 million have a computer science degree. The other 10 million just somehow do things. But they do things. No, they do things, guys. That's important. They do things, right? And that's where the automation and the declarative is coming out, because you got a lot of guys who are, doing SQL, and, they don't really know to write the most complex algorithm or the most complex scalable distributed system. But that's where the things matter at the end when you talk to the masses. And I can perfectly see a future where you got not only the primary operational system, but also all your secondary analytics applications running out of JSON-based systems. I'm really disappointed that still the state of technologies that I see in many companies, here is my operational store, that I'm using Couchbase because I cannot achieve scalability in any other way, and then I'm putting it into a column database, offload to a column database to achieve performance. There's really no fundamental reason for this to happen. So I think in the future, it would just not be happening. I mean, you can basically have it all in a single JSON-based system. And that is the takeaway message.